Okay, so that's it for the optimal income tax part of the class. Now we'll talk about a much more empirical set of issues, which are kind of estimating the key parameters that are relevant for these optimal tax models. So there's this is a huge, huge literature. I will give you, we'll talk about it in several steps, okay? So first, we're just going to talk about broad methodological issues in estimating the relevant labor supply elasticities to think about optimal policy. We'll then spend quite a bit of time on a technique called nonlinear budget set methods, which accounts for the fact that the budget constraint is not a straight line, but you have progressive taxes, and what that does to estimating elasticities and how it creates opportunities to estimate elasticities. I'll then give you a quick summary of what elasticity estimates actually look like in static models. So like, what are the numbers people get? What are the research designs they use? We'll then talk about intertemporal labor supply models. So important distinction in literature. Static models are, one period models. We're thinking about labor supply and how it responds to changes in tax rates in a single period, or more generally, a permanent change in tax rates. Intertemporal labor supply models, which are actually the more general and more appropriate, I think, labor supply model, are dynamic ones where it's like a life cycle model, and when tax rates change in one period, I might substitute when I work across periods. Then we'll talk about elasticity of taxable income, connecting back to that Feldstein paper, which we mentioned earlier. We'll say a little bit about micro and macro elasticities. There's a whole separate macro literature on estimating these elasticities that's highly relevant for the business cycle literature and growth literature. And then I'll end by talking about some implications for preference parameters, which ties a lot of this reduced form empirical work back together to the structural model that's underneath. Okay, so it's a huge literature in terms of papers, and also there are lots of surveys of this literature. So going back to '86, there are surveys in the Handbook of Labor Economics, and then that's kind of been updated over the years. In public economics, this one is good on the nonlinear budget set methods. This has more recent stuff, including taxable income elasticities. On the taxable income stuff, the Saez and co-authors' recent JEL article is the best comprehensive summary.
Are there big differences in the labor versus public?
Yeah. So we'll talk about that. The labor stuff, so Pencavel's stuff mainly covers intensive margin hours responses. So the key distinction is public has moved totally to taxable income as a measure of how you calculate responses. Labor traditionally has focused on hours of work and whether you're working or not. So Heckman talks quite a bit about extensive margin responses, as do Blundell and McCurdy, but none of these guys are using earnings or taxable income to measure the size of the response, and that has costs and benefits.
Is that because the public side is more concerned with welfare analysis and the labor side is more interested in the responses that are
Yeah, that's right. I think it's also the public literature has developed a little bit more recently when people have started to use tax data more, and this literature has kind of shifted into public from labor. You'll see relatively few pure labor studies on the impacts of taxes on labor supply. Now, the taxable income thing, earnings, is definitely the prominent approach. So you'll see the evolution of this as we go through the literature. Okay, so at a high level, what are we trying to do? We know that the labor supply elasticity is a parameter of fundamental importance for income tax policy. Optimal tax rates depend inversely on this Hicksian elasticity. And so what we're going to first do is discuss a bunch of econometric issues that arise in estimating these elasticities. As well, I should emphasize, in any other price elasticity, actually, there's nothing special really about labor supply. It's just that this literature is so developed. But, many of you may work on other topics like, savings or whatever else, and you will see that the same econometric issues will matter there. So definitely useful to pay attention to what the methodological issues are here, as well as how they matter for labor supply. So just to be organized about what the econometric problems are, I'm going to start with a very simple labor supply model that helps us fix ideas. So I'm going to make the following assumptions. First, we have a single period, so it's a static model. Second, it's intensive margin, so we're getting rid of the fixed cost stuff that was in the Saez paper that we talked about. One-dimensional choice, so what I mean by that is it's not like the Feldstein case where you had multiple dimensions of labor supply and then you look at taxable income. Here you're just picking hours of work. Third, no frictions or adjustment costs. So one of the key issues that comes up in this literature and is really at the frontier of the literature now is that people are not able to easily adjust their hours of work when you change policies. And that messes up the estimation of elasticities in various ways. We're going to take that off the table for the moment. And we assume a linear tax system. Let's let C denote consumption and L the number of hours you work. Normalize the price of C to 1. We assume the standard quasi-linear form for the utility function, and this convex disutility of labor, which is going to generate a log linear constant elasticity of labor supply function when we maximize utility. The agent earns a wage of W per hour of work and has Y in non-labor income. So with this utility function, you're going to get log L equals A plus B log W times 1 minus T, where T is the tax rate. But with a more general utility function, you're going to get an expression that depends upon both non-labor income and wages per hour of work. Okay, so with a tax rate of tau and labor income, the individual is going to solve the standard utility maximization problem. Just reviewing what I said, you have this first order condition that generates this log linear labor supply function, right? Yeah, I think I'm missing a log on the left-hand side there. Should be a log L there, sorry. Because it's log labor as a function of log of the net of tax wage. Okay, so here, unearned income doesn't matter because utility is quasi-linear. If you have a more general version of this, you can derive a log linearized version of the labor supply equation that's going to be a function of the net of tax wage as well as your unearned income, okay? And then you can use the Slutsky equation once you estimate both epsilon and eta, log missing here as well, sorry about that, to recover the compensated elasticity that we care about for optimal policy, okay? So that's our objective, and we're going to talk about various issues that arise in accomplishing that objective. Yeah?
Is the functional form assumptions matter here at all?
No, I mean, they matter in the following way. So typically, the way this is implemented econometrically is that we estimate a single elasticity. Okay, so this functional form is going to generate an elasticity that does not vary with the tax rate or the wage. In practice, that may or may not be true. It could be that elasticities fall as wage rates get really high or not or whatever. So we often end up estimating like this log linear regression, largely motivated by just empirical tractability. And in the back, you can think of that as coming from this utility function. But the more general version of this, if I could do the thing totally non-parametrically, I would estimate the elasticity at every tax rate, just separately, right? And I'd have this function that shows me what non-parametrically L looks like as a function of tau. Here I'm imposing that it has a particular log linear shape, but there's no deep reason to do that. Okay, so there's a long list of problems with OLS estimation of that labor supply equation that people have worked out over the past 30 years. So here's a list, and then we will go through each of these in more detail. So the first are a whole bunch of econometric issues. First, you have unobserved heterogeneity, and what I'm showing you in brackets, use this as kind of a reference once we go through this. In brackets is the solution that's been proposed for each of these problems. So unobserved heterogeneity means that people with different wage rates have different characteristics that might directly affect their labor supply. And so if I regress L on W, I'm going to get a biased estimate. Usual way to deal with that problem is to use taxes as instruments. There's another issue of measurement error in wages and what's called division bias, which creates further econometric problems, which we can also solve with tax instruments. There are selection problems that arise, going back to the work of Heckman, where you can address them using panel data. I'll go through each of these things in more detail. Then there's the issue of extensive versus intensive margin responses, for which people estimate participation models rather than just pure hours of work models. There are concerns about non-hours responses. That's the Feldstein 1995 issue. that people may be responding in terms of effort or other things. And so for that, we look at taxable income instead of hours. So that's the modern public finance literature. There's the fact that the tax system is actually progressive and is not a straight line. The budget set is not a straight line. So progressive taxation, the way we deal with that is nonlinear budget set methods. That goes back to the work of Hausman. And then there's the recent issue that people have been spending a lot of time on, which is frictions. That is, when we apply conventional methods, we don't recover the true elasticities because people don't change in the short run. And there are recent approaches like bounds and macro type of comparisons that try to get at that. So let's go into more detail on each of these. So problem number 1, unobserved heterogeneity. So this is a standard problem in any empirical work, basically. Early studies of labor supply, like going back 40 years, estimated the elasticity just by regressing hours of work on wages. So it's like I have this cross-sectional data set. Some guys have higher wage rates than others, regress hours on wages. Okay, so that is not a good idea because there's no research design, basically, right? So you have unobserved heterogeneity. Those with high wages are likely to have a high propensity to work for other reasons, right? There's some reason you have a high wage. It's not random. You might have gotten a lot of education. Maybe that means you're really motivated, whatever. And that's going to create a cross-sectional correlation. That's going to create a correlation between the error term epsilon and the wage rate. And as a result, just the cross-sectional correlation between these two things is likely to yield an upward biased estimate of the wage elasticity. So what's the solution to that that's used in the modern literature? Don't just use variation in W. Use variation in 1 minus tau times W, where you're instrumenting with tax reforms or some other source of variation in tax rates, which makes a lot of sense. The second problem is related, and this arises from a data issue, which is actually goes back to mainly the labor literature, which is that we typically don't directly observe wages, right? So often in data sets, what you have is information on the number of hours you work and how much you earned. And then there's obviously an identity, divide earnings by hours to figure out your implied wage rate. That is really problematic. And this is a general warning for empirical work. Like, do not construct variables as a function of other variables and then include them in your regression. So you'll see here what the problem with that is. So when you have hours measured with noise, which is very plausible, right? People tell you with error how many hours they work. That leads to what we call division bias. So let's let L star denote true hours. So that's the number of hours you actually worked. And L, the number of hours you told the surveyor you worked, okay? We define W as E divided by L. That's crucial, not E divided by L star, all right? Where E is your earnings. And so we can write log L as log L star plus mu. That's the measurement error in reported hours. And so as a result, log W, which is just log E minus log L, all right, is log E minus log L star minus mu, which is log W star minus mu, where W star is your true wage. So my imputed wage also has measurement error arising from the fact that you misreported your hours. That makes sense. Okay, so now what's the problem? That is going to create a spurious link between hours and wages, even if there's no true elasticity. Basically, the problem is that when you run a regression like this, if you constructed this variable from what's on the left-hand side, you now have the same error term on the left and right-hand side of this equation. That is, you've effectively introduced a correlation between the left and right-hand side variable, right? So what is the expected value of beta 2? What is that going to converge to? It's going to converge to, we know from the OLS formula, to the covariance of log L with log W divided by the variance of log W. But the problem is log L has this error term plus mu in there, and log W also has that error term of minus mu. And so now you're going to get a thing that does not converge to the covariance of log L with log W, no matter how much data you have. You're going to have this additional variance of mu term in the numerator. Okay, so that's mathematically what the issue is. What's going on? The orthogonality restriction for OLS is being violated. And one way to think about it intuitively is that workers with high misreported hours are also going to have low wages, right? So if I accidentally told you I will work 80 hours a week, I'm going to also accidentally conclude that your wage is really low. And that's going to induce this negative spurious correlation between the left and right hand side variable, which is actually a very common problem in empirical work, not just here. So how do you solve this problem? Again, you use taxes as instruments. This is like going back to the classical use of instrumental variables to deal with measurement error. You instrument for the endogenous wage with tax rates. If you measure that properly, you don't have this problem. Okay, is that clear? Let's talk about the third problem in the next lecture. So I'll stop there. So just to remind you guys where we were at the end of the last lecture, we're talking about estimating labor supply elasticities using a log linear specification that looks like this, right? So we're regressing log hours on log wages, and we're interested in that coefficient beta, or B, that is going to tell us the labor supply elasticity that we're interested in, right? So we're talking about various problems that arise when estimating that equation, which have been discussed at length in the literature. And so at this point, I'm just describing what the various problems are and what types of techniques people use to address those problems, and then we'll go into detail on each of these issues and discuss the modern literature. So we talked in the previous lecture about division bias as one of the issues that arises because of measurement error. Another problem that arises is selection. So suppose you have fixed costs of working, which we think are plausible, right? So there's some fixed costs you have to pay when you enter the labor force. And so as a result, many people decide not to work at all. They work 0 hours. So they're not at an interior optimum. So in that case, the econometric problem that arises is that you don't see wage rates for non-participants, right? So you only see a person's wage rate, even if you're imputing it by dividing earnings divided by hours. Because h equals 0, you don't have an estimate of the person's wage rate. And so that creates a classic selection problem, what motivated Jim Heckman's famous 1979 paper, which generates the problem that an OLS regression on the subsample of people for whom you have wages, that is on the workers themselves, is going to generate biased estimates because you're only going to include the guys with Li greater than 0. So what's the intuition? This biases OLS estimates really in two ways. The first is if you're just trying to measure the intensive marginal elasticity. So what is the elasticity of hours of work with respect to wage rates for the people who are already working? Even that parameter is biased because in order to select into the labor force when you have a very low wage rate, you must have something special about you that makes you want to work, even if you're getting paid only $2 an hour, right? You must have a high unobserved taste for work, which means that you're going to have a high level of hours, a higher level of hours than the average guy who would have a wage rate of $2 an hour, right? And so as a result, what that's going to do is it's going to attenuate your estimated labor supply elasticity. So rather than getting a steep upward sloping function, the guys at the very low wage rates are going to have unobserved high taste for labor supply, and you're going to end up misestimating even the intensive marginal elasticity. A second problem that arises, which is more obvious, is that you don't capture the extensive margin response. So when wages change, you not only change hours of work conditional on working, but you also change the fraction of people who are working. So I will come to that second problem in a minute. But the first problem, which is what Heckman was focused on, is how do you measure, you can think of it as how do you measure the intensive marginal elasticity when you only observe wages for the guys in the labor force. Heckman's solution was a parametric selection correction. So this, I'm not going to go into this in detail, but the idea is that you make a distributional assumption on what wages look like. So like you assume normality. And then what he shows is in your estimating equation, if you include what's called the inverse Mills ratio, you can correct, it turns out that you can exactly correct the selection bias under that normality assumption. Now that idea, I think, was very influential in making people recognize that you had to deal with this problem. But that particular solution is highly dependent upon the functional form that you've assumed, that normality assumption. So I don't think that's a credible way to correct for selection in the modern literature. How might you go about it while imposing less structure on the problem? Well, really, fundamentally, the problem arises when you have a cross-section, because you can't figure out when you change wage rates. If you only have cross-sectional variation, there's basically a compositional effect. So different guys show up in the labor force, and that ends up creating bias. So one non-parametric approach to dealing with this problem is to use panel data, right? So suppose I follow a given person over time, and I see his wage rates fluctuating. Then I know it's not that I'm comparing a high wage and a low wage guy who might have different unobserved tastes for work. As long as your unobserved tastes for work are not also changing over time with the wage rate, then I get a consistent estimate of the labor supply elasticity, okay? And so that's part of the reason I think a lot of the recent work has shifted towards panel data or towards other type of estimators where you're not biased by the selection issue, which we'll talk about later. Okay, questions on that? Yeah, so that's going to relate to the next thing that I'm going to talk about. So somebody who's, let's say, not working their entire life, there's no meaningful notion of an intensive marginal elasticity for that person. So if we're estimating intensive marginal elasticities, this ties back a little bit to like the sufficient statistic literature. That is, what the elasticities that matter if you're setting optimal tax policy are for the people who are actually in the labor force at some point, right? The unemployed guys are of interest because when you change wage rates, they might end up, entering the labor force or leaving the labor force. And so that's the other margin that I want to talk about now, which is the extensive margin. So when you have these fixed costs of work, you also want to characterize the effect of taxes on the labor force participation decision. So as we saw, like in the context of thinking about the EITC, the Saez 2002 paper, a key question is how large those extensive marginal elasticities are relative to the intensive margin, right? So you also want to be able to estimate these. The idea is that when you have fixed costs of work, people may jump from non-participation to part-time or full-time work. So what we saw in the Saez model was just the assumption that you could only make discrete choices in the simple version we discussed in the lecture. But the more general version allows you to pick your hours continuously, but you have to pay a fixed cost that might vary across people to enter the labor force. And that's going to generate this pattern where when I change wage rates by some small amount, a bunch of guys jump from 0 to 15 or 0 to 30 or whatever, right? So how do you handle that? That's actually more straightforward. So what's kind of interesting is in a cross-section, I think this is something people don't always appreciate. In a cross-section, when you find extensive margin responses, that immediately makes it much harder to correctly estimate intensive margin impacts. Because when you have an extensive margin response, you know that you have a selection problem. That is, when I raise wages, there's a different set of people in the labor force. And so that's going to complicate the estimation of intensive marginal elasticities, okay? But the extensive margin is actually, in a sense, easier to get at because all you do is just regress the probability of whether you're working or not, like an indicator for work, on the wage rate or use tax instruments, include unearned income. So the usual stuff on the right side, but the left-hand side variable is a discrete 0-1 variable. And then you can have various types of functional forms. So commonly people will either use a linear probability model. So phi here would just be the identity function, or like a probit where phi would be the normal CDF, right? So that you don't get probabilities going below or above, below 0 or above 1. But the logic is basically the same. One thing that is important to note with extensive marginal elasticity estimation is precisely because you don't see wage rates for the guys who are not working, this thing only makes sense if you have variation in tax rates, right? So the way to think about it is how do tax rates affect the fraction of people who are working? I don't need to know anybody's wage to answer that question. And that elasticity of the fraction of people working with respect to the net of tax rate, 1 minus tau, is exactly what's relevant for optimal tax formulas like the EITC, Diamond Saez type of stuff. Okay. All right, so additional now, moving on to other issues that arise in estimating this very simple version, which is what people started out with. So the traditional labor economics literature focused purely on hours of work and labor force participation. So those were the two margins people looked at. As we've talked about previously in this class, the problem with that approach is that income taxes might distort many margins besides hours of work. This is the Feldstein insight in 1995. And the more important responses may be on these other margins. And moreover, hours are very hard to measure, right? So most people just report 40 hours a week, even though they're actually working a different amount. So there are two solutions in the modern literature, which we'll talk about in more detail. We talked about the logic of the Feldstein result in the context of deriving a sufficient statistic formula. We'll talk about the empirical work in this part of the class on taxable income. So, right, so one idea is use taxable income as a broader measure of labor supply instead of just hours of work. The second approach, which I'm not going to spend a lot of time on in this class, but actually is quite active as a literature, is focusing on subgroups of workers for whom hours are better measured. So one example is this literature that's emerged on taxi drivers, because for taxi drivers you can measure their hours of work relatively precisely, and they can adjust their hours of work relatively easily, which is actually quite important. And so there are 4 or 5 papers in top journals in the past few years debating how changes in wage rates affect taxi drivers. And how do you have changes in wage rates? Because conditions change, like if it's raining, more people want to take cabs. And so in effect, for every hour you're out on the street, you have a higher wage than at other times. So you have good instruments too. The reason I'm not going to spend a lot of time on this in this class is something we'll talk about later. The frequency of the variation that you're using matters a lot for which elasticity you're identifying. So initially, we're going to talk about a static model where there's no notion of the time over which wages are changing. But if wages are changing at a very high frequency in an intertemporal labor supply model, which we'll come to later on, essentially what you're identifying is the degree to which people are willing to substitute across days in terms of how much they're willing to work, which could in principle be a very different parameter than what you care about for tax policy, which is what happens if I have high taxes, like forever or for several years, right? So I think that's interesting from an empirical point of view, but less relevant in terms of the parameters we're actually trying to estimate for policy. Okay, another issue, which we will actually talk about quite a bit in this lecture, is the fact that in the standard linear regressions people were running traditionally, they're assuming implicitly that there's a single linear tax rate that people face. But we know in practice that the income tax system is actually nonlinear. That is, people face a progressive tax system. And so that matters a lot, actually, for estimation. It both creates opportunities to estimate elasticities, because it creates additional variation, and it complicates what you get out of running regressions like this. So just to show you what this looks like in practice, right? This is very important. So this is a depiction of what the U.S. income tax schedule looks like before and after the 2001 tax reform for a married couple with 2 kids, okay? And all I want to show you here is implicitly what you're assuming when you run a regression only using the guy's marginal tax rate is that he faces a constant marginal tax rate at that local level. And you can see that that is incredibly far from the case in the US tax schedule, right? I think, like by some calculations, there are 27 different kinks or something like that. And depends in all kinds of ways upon your income and deductions and so forth. So you're not even close to being approximately right if you assume a locally linear budget set, okay? And so, we'll come to what that does, but let's just first talk graphically about a few different examples of the types of nonlinear budget sets that we think about conceptually, right? So this is the tax system in practice. This can sort of be seen as a combination of the various examples I'm going to show you here. So the way people typically depict this is, say you have hours of work or hours of leisure going to the right on the x-axis, okay? So we start out here with 0 hours of work, And then as I come this way, I have less leisure and I'm supplying more labor. And then think of this as like working 24 hours a day. And then this is the amount of consumption or income that I have. Consumption equals income in what we're talking about here because this is the static model. There's no scope for savings. Okay, so what does the nonlinear budget set look like? Let's say you have a progressive income tax and you have nothing else like the EITC, nothing else on top of that. So initially, you get a very high rate of return to every hour of work. Then you move into a higher tax bracket and that becomes flatter. Then you move into a still higher tax bracket and the rate of return to work becomes even flatter and so forth, okay? So that's what a progressive income tax, simple progressive income tax is going to generate a convex budget set that looks like that, okay? And we call each of these points convex kinks, which I will distinguish from non-convex kinks in a second. Okay, another second example which we talked about, the EITC. What does that look like graphically? So your wage rate, let's say, is given by this line here. What the EITC does is it makes your wage rate higher initially. Then there's the plateau region where the wage rate is the same. Then there's the phase-out region where the wage rate falls below what your pre-tax wage is. And then you have this non-convex kink, okay? Non-convex kink refers to this shape in contrast with the convex kinks shown here, okay? And then you continue along, let's say, with no tax distortions. So why do we distinguish non-convex and convex kinks? Because optimizing theory predicts that there should be a collection of individuals who choose to locate at these convex kinks because your wage rate is dropping discontinuously at those points. And so a lot of people should decide that they want to quit working at exactly that point. In contrast, the non-convex kinks are dominated points. So if you think about drawing an indifference curve on this diagram, that is going to be a strictly dominated point. You'll always do better if you're a little bit to the right or a little bit to the left. So you should see a hole in the income distribution around the non-convex kinks. This stuff matters because when we start estimating these models, those are the type of properties of the distributions that are going to identify what the underlying elasticity is that's generating the data. A couple more examples that we see in practice. Social Security payroll tax cap. So what is this? In the US, you pay a Social Security tax up to some threshold, like around $110,000. And then beyond that point, you're exempt from paying Social Security taxes on the marginal dollar. Okay, and this is one of the key things that people are debating in order to close the budget deficit. Should we remove that cap or not? So what does that do to the budget set? This creates a non-convex kink, right? Let's say this is the Social Security payroll tax cap. Until this point, I had a lower wage because I was paying 6% to the government on the margin on every dollar that I earn. And then at that point, the wage rate goes up when I cross $110,000. So the marginal tax rate actually falls when I cross that threshold. And then a last example, negative income tax. So negative income tax is the kind of thing that would be predicted to be optimal in the Merleesian model, not the model with fixed costs. So this is a very extreme version of a negative income tax where I give everybody a grant of 0. And then I have a 100% marginal tax rate, which I'd never want to do in practice, until they reach some hours threshold, at which point I impose no tax at all. So the idea is if you're earning less than $10,000, I just hold your post-tax income fixed at $10,000. Every extra dollar you earn, I take a dollar away from you in the size of the grant. And then once you cross 10,000, then you just go up with your earnings beyond that point. That's going to generate a shape like that, and again creates this non-convex kink here where presumably you don't want to locate. And also because marginal tax rates are 100% here, you're not going to want to be in that region either in that particular case because it's dominated, right? You always want to be to the right side on this diagram because you get more leisure and more earnings. So you'd be strictly better off being here than being anywhere to the left. Okay. All right. So so what did those types of shapes of budget sets? What do they do to the econometric problem of estimating labor supply elasticities? So they create two problems. first, they generate model misspecification. Basically, when you assume that the budget set is linear, you have misspecified what the constraint actually looks like. And that is going to create create a problem in estimating the elasticity epsilon through two sources, okay? First, you're going to underestimate the degree of response because people pile up at the kink. So let's go back to one of these examples. Let's say this one. So when I run a local linear regression with just the marginal tax rate, okay, so let's say the marginal tax rate in this bracket is 40%, and it goes up to 50%. So what I do, let's say, is run a regression of hours of work on the marginal tax rate that people face using this reform which increased tax rates from 40 to 50%. So suppose I estimate that, you know, people reduced hours by 10% or something like that. What I should end up seeing is that for lots of people who were right, you know, close to this kink point, they should never drop into the previous bracket because nothing changed in this bracket below. So they should just be piling up at point 2 here, right? At this kink point. And so as a result, if I just regress hours of work on tax rates, I may not find that much of a change, but that doesn't mean that the elasticity is small. It's just that they've hit the corner, okay? And so you can see why that's going to lead me to underestimate the elasticity. Okay, so that's one problem. Now, you can see that this problem is going to be less severe if I'm very far away from the nearest kink. So if I'm looking, let's say, at these guys, and I've pivoted this budget set, then this issue of running into the kink is not such a big deal, and maybe I roughly get it right. So you can formalize that argument. As you get further away from the kink, this first problem that I'm describing is going to disappear. But there's a second problem, which is that you're going to misestimate the income effect. So if there are income effects, what matters is not just your marginal tax rate, but also your unearned income, right? So we know that the labor supply function, if we're trying to recover the compensated elasticity, depends not just on your current marginal tax rate, but the total amount of net income you have at the current point. And the net income you have is going to be a function not just of your marginal tax rate in the current bracket, but what was going on in the previous brackets as well, okay? And so if you ignore that, you're going to again end up misestimating the compensated elasticity, and I'll show you exactly how that arises in a second. So this was an insight of Hausman in a paper in 1981 where he develops this method of estimating elasticities with nonlinear budget sets. So basically, you're going to get the income effects wrong if you pretend that the budget set is linear when in fact it has an intercept, which makes sense. You're miscoding the guy's unearned income effectively, all right, if you pretend the budget set is linear. The second problem, so I see this as kind of like you've misspecified what the actual model is, okay? You've misspecified the budget constraint. The second problem is that you have a further source of econometric bias because you have essentially a reverse causality problem. So suppose you are using taxes as instruments, right? Which is what we decided is a solution to dealing with all these measurement error problems. So the issue now when you have nonlinear budget sets is that tax rates are no longer just fixed and determined exogenously by the government. They are a function of how much you're working. So now, you know, usually we think of tax rate affecting labor supply, right? But now you also have labor supply affecting the tax rate because the more you work, the higher the tax bracket you're in. And so that form of reverse causality is going to create bias in your elasticity estimate if you just ran a naive regression of hours of work on tax rates. What's the intuition? Tastes for work are going to be positively correlated with tax rates, right? The higher your unobserved taste for work, the greater the tax bracket that you're going to be in, right? The more you earn, the higher the marginal tax rate you're going to face. And that's going to create a downward bias in an OLS regression of hours of work on net of tax rates, okay? So the solution to the second problem is to use an instrumental variables approach, where you isolate the variation in the tax rate that's due to reforms, right? So suppose you have two sources of variation in tax rates. One that's coming from the cross-section, so guys are at different levels of hours of work. That's not variation in tax rates that you want to use because it's collinear with unobserved tastes for work. But suppose there's a second source of variation in tax rates which comes from the fact that I changed tax rates in some bracket, right, like the 2001 tax reform or whatever. I want to isolate that source of variation, and the way I do that is with an instrumental variables technique. Okay, so we'll talk about how you implement this. It's a straightforward methodology that Gruber has pushed in recent work. Okay, so just to be clear, the second problem can be resolved using a standard instrumental variables approach. The first problem is deeper than that. You actually have the wrong model, and so it requires a fundamentally different estimation method, and that's really what we're going to focus on in this lecture. Yeah.
Can you explain?
Okay, so the first problem of dealing with the fact that the budget set's not linear requires a fundamentally different estimation method, all right? Which is what we'll talk about in this lecture. That's the Hausman nonlinear budget set approach. Let me mention one last set of problems that arise in estimating the simple linear equation or nonlinear budget set approach, which is really, I think, one of the central areas of focus of the current literature, and will give us a lens to think about what people have been finding. So the standard methods, whether linear or nonlinear, assume that people can costlessly adjust hours of work. All right, so we're assuming that when I change tax rates, you can flexibly, tax rates go from 35 to 40%, you can cut hours of work just continuously. In practice, we know from the data that most hours changes actually occur when people switch jobs. And moreover, as we've talked about in previous lectures, many people actually seem to be inattentive to changes in tax rates even when they do occur. Okay, so the way I like to think about it is there are various sorts of frictions that prevent people from reaching the optimum. These might be attention costs, these might be actual search costs of switching jobs, they might be other types of adjustment costs involved in changing hours of work. What is the important consequence of that? Again, remember that the type of approach we're taking here is we're able to estimate reduced form parameters using various types of quasi-experimental variation, but our ultimate target is not just those reduced forms, but the elasticities that enter these optimal tax or optimal policy formulas, right? And so the issue that arises here is that really, in a sense, what you care about is not per se the impact of some reform on hours of work or taxable income before versus after that reform. What you care about is the long-term impact, right? So at the end of the day, we want to know what would the impact on the US economy be if we had a very progressive tax system versus if we have lower tax rates. We don't really care about the response within a couple of years. And intuitively, because of these types of frictions, you worry that the long-term impacts of policies might actually be much greater than the short-term impacts that you observe in the data because people don't react the year before versus the year after a reform. They don't react quickly, okay? And so just to formalize what that problem looks like and what it might do to estimates of elasticities, let me talk through this recent paper. So this is the Econometrica one, which is on the syllabus. I'm just going to describe the basic setup here, and then we'll talk about what this paper actually does later on. So what this paper does is formalizes how the types of frictions I was just describing affect the identification of elasticities. So all I want to talk about here is just a framework for thinking about how the reduced form elasticity we're able to estimate as econometricians maps to the elasticity we're interested in from an optimal policy perspective. So here's the simple idea. Let's assume that people can choose any level of demand xt. So I'm writing this in the context of demand for a good, but as we've talked about many times, that's totally equivalent to choosing labor supply, okay? So let's say I can choose demand for a good xt that generates a utility loss less than some exogenous threshold, which I'm going to call delta. So the idea here is rather than assuming that people pick the utility maximizing point, which I'm going to call xi star, I'm going to require that people make a choice near that utility maximizing point. So for those of you who've taken a macro class, You know that this is very similar to the literature on near rationality or menu costs, which requires that people make choices near the optimum rather than at the optimum, okay? And so the way I'm thinking about the frictions is, frictions might affect your behavior because it's not worth it to re-optimize your demand or your labor supply in order to get, let's say, a 1 or 2% gain in utility. But if you can get a massive gain in utility, then you might actually pay attention and you might actually switch jobs and you might re-optimize, okay? So this is a simple way to capture that. And I'm gonna measure, so think about it just for simplicity in the context of quasi-linear utility so that we can measure utils in dollar terms, okay? So it's a money metric. And I'm gonna require that the size of that utility loss is less than some threshold, which I'm gonna specify exogenously, okay? I'm gonna input that into this exercise. And it turns out to be analytically convenient to measure the size of that threshold as a fraction of the amount you're spending on the good. So PXI star is the optimal expenditure on good X, okay? And delta is a percentage of that. So to take a concrete example, suppose you're spending $20,000 on a car at the optimum. If you have a delta of 1%, then I'm allowing you to make a mistake that costs you up to $200 in terms of utility. This is just a way to scale the size of the utility losses you're allowing the agent to tolerate. You could scale it in other ways. It turns out to be analytically convenient to scale it by the expenditure, okay? So then what you see immediately is that everything works in terms of sets rather than single points. So if I give you a price P, a price vector P, normally the way we think about it in economics, in neoclassical economics, is that it maps to a single point that the agent chooses from utility maximization, right? And then we think about how to recover what the utility function looks like or what the elasticity looks like given the points that we observe. Here, because I'm specifying, I'm putting less structure on how the agent actually chooses, right? I'm saying he can choose any X that satisfies this condition. That's going to map to a choice set, which I'm going to call X of P delta instead of a single point. So just to see it graphically, think about, suppose I have two goods and I plot utility as a function of the amount you're consuming of good X. If you were optimizing, you'd pick that point there, right? That generates the maximal level of utility. This is for a given fixed price, right? So, and I've got demand on the x-axis, right? So what I'm saying is, instead, to model what frictions do, we require that people choose a point that generates utility above this threshold, okay? So they're allowed to tolerate some loss. And the key property of this, which we'll talk about later, is that because any smooth function looks locally quadratic, that is the utility losses, it's locally flat, right? So the utility losses of deviating from an optimum are second order, they're small. The consequence of that is even if I allow a very small threshold here, I'm going to generate a wide choice set here. So I don't need to be that close to the optimum in order to generate utility that's very close to the maximum. That's basically the logic. And so what that's going to do then is I have, let's say, this 1% threshold. That's going to map to some set of choices that I'm going to make given a price vector or given a tax system. Okay, so now given that setup, we can think about how these frictions affect the identification of elasticities as follows. So let's look at this graphically. So let's say that the true underlying elasticity, the term that people are using nowadays for this is the structural elasticity, is, let's say, epsilon equals 1 in this example. So this is an example where I've got demand for some good X. I'm varying the price of that good, and the dashed blue line shows me the demand curve that I would estimate if there were no frictions. Okay, so in a frictionless world, the guy actually has a utility function that generates a price elasticity of 1. In practice, because of these frictions, all we know is that he's going to make some choice within these red intervals at these two different price levels, call them PA and PB. So let's say this is at a price of 1, this is at a price of 1.2. The only information I'm imposing on the problem is that you pick some point near the optimum, determined by what I showed you on the previous slide. So essentially what I'm doing here is taking this red interval and flipping it on its side at two different price levels, right? And so All I know is that you're picking some point within this set at this price and within that set at that price. So now let's think about what that does to actually estimating elasticities. So I'm going to show you various black lines which correspond to what I might see in the data when I change prices by 20%. So the first thing that you can see is that I could well see a zero response, because the only restriction I'm imposing is that you have to be close to the optimum both before and after the price change. And so with this particular numerical example, even though the underlying elasticity is 1, I could end up seeing a zero response because you're close to the optimum both before and after, even if you don't respond at all in that particular case, right? You could actually end up seeing an over response. So what's the intuition for why frictions might do this? So think about an example where, let's say you have a sequence of tax changes, and a bunch of tax changes have occurred in the past that pushed you very close to the threshold of adjustment. And now you have this last tax change that's kind of the straw that breaks the camel's back, where you say, okay, I've had enough, like my wage rate has gone down so much, I'm going to make a big adjustment. So I can end up having an overreaction relative to the underlying structural elasticity. The way this is set up, you can even have a wrong signed response, because I'm not imposing any structure on the problem, and we'll talk about what this does later on when there's a method one can develop to bound elasticities using this approach, which is what I do in this paper. But the point is, there's a whole array of black lines that could be generated by a given blue line as soon as you have these frictions. And that's really, I think, a fundamental challenge in going from the elasticities we're able to estimate to the blue line that we're trying to identify. Okay, so all I'm doing here is just posing what the problem is. I'm not going to talk about exactly how we solve that here. So just to restate, the identification problem, the way I see it, is that you have multiple observed elasticities, which I'm going to call epsilon hat, can be generated by a model with a given structural elasticity, which I call epsilon, when you have delta greater than 0, when you have these frictions. And so conversely, because of this, there are multiple structural elasticities consistent with a given observed elasticity of epsilon hat. So suppose you run that regression and you find an elasticity of 0.1. What this is showing you is that you can't really have a lot of confidence in going from that 0.1 to a statement about optimal tax policy, because who knows what would happen if we had like a European type tax system versus a US type tax system for many, many years, right? You might end up having very different behavioral responses. One thing that I want to stress is that this is not a problem about inference. That is, it's not a finite sample problem. It's a problem that relates to identification. So what we mean by that is it doesn't disappear as the sample size approaches infinity. So even if you had an arbitrarily large amount of data, you're still going to get the elasticity wrong if you have these frictions. And so as I was saying, this, as you'll see, as we go through the various parts of the literature, is an important focus of current research. How do you actually recover the underlying elasticity? And I don't think we've quite figured out the answer yet. Just to be clear on the roadmap here, I've described a bunch of problems that arise in estimating elasticities. Now I'm going to step back and show you how the literature is developed in addressing each of these different problems. So we're going to go step by step. So I'm going to start by discussing literature estimating intensive marginal elasticities using variation in tax rates for identification. I'm going to start with the case where we have progressive taxes and talk about how we estimate elasticities in that case in models without frictions first. Okay, so forget about the frictions issue for now. We'll talk about how that ties into this a bit later. So we'll first discuss the traditional nonlinear budget set estimation using maximum likelihood methods, which is the work that was done in the 80s and 90s. And then we'll discuss what I think is the active part of this literature now on bunching estimators, which are more in the spirit of this non-parametric sort of identification that we see in recent work. And then we'll talk about what's really, I think, the frontier, which is work on frictions and bunching estimators and how you can recover the underlying elasticities from the amount of bunching. So the nonlinear budget set methods pioneered by Hausman, I think, are useful to understand at two levels. First, because this is actually a sensible approach to estimating these elasticities if you buy the structural assumptions, but also because they're a good illustration of maximum likelihood methods, which we don't see very much in applied micro. And so I think it's good to just be familiar with how it works if you end up implementing such an estimator. This is like a classic example of maximum likelihood estimation. So here's how it works in Hausman's setup. So we assume some specification for an uncompensated labor supply equation. So you can think about it either as I derive that functional form from a utility function, or I start with that functional form and show that it's consistent with some utility. That's like the recoverability idea. Okay, then labor supply is going to be a function of wage rates, net of tax wage rates, income, and there's some unobserved heterogeneity, nu I, which we're going to assume has some distribution, typically a normal distribution, which say has a variance sigma squared. In the data, what we see are wage rates, tax rates, unearned income. Okay, so when I say unearned income, I mean like, you know, an inheritance or like interest income, capital income, something that is not related to the number of hours you're working. And LI, the number of hours you work, okay? So let's first, the econometrics of this look a bit complicated with a lot of equations, but the concept is actually really simple. So there are two steps. First, we construct a likelihood function given the observed labor supply choices on the nonlinear budget set. Then we find the parameter vector that maximizes that likelihood. So the way I like to think about maximum likelihood is give me a set of parameters, like propose a set of parameters that might be generating the data, like an elasticity, like some slope with respect to unearned income, an intercept, a distribution of variance, etc. Given that set of parameters, I can calculate how likely it was that I saw the data that I did given that parameter vector, right? Now it's just like a looping problem. Give me another parameter vector, give me another parameter vector, just cycle over all the parameter vectors, calculate the likelihood, in some sense the probability of seeing the data given that parameter vector, and find the one that is the maximum likelihood, the most likely. That's the maximum likelihood estimator of the structural parameters, right? So very simple concept. So one important insight that Hausman had, which relates to the problem I was describing about misestimating income effects, is that you need to use virtual incomes instead of actual incomes when you have a nonlinear budget set. And so let me just illustrate what that is with this diagram. So when you're thinking about modeling a person's labor supply decision as a function of his marginal wage rate and his unearned income refers to the amount of income you would have if you worked 0 hours. You need to incorporate the fact that if I linearize this segment of the budget set, its intercept is not going to be given by y1, its intercept is going to be given by y2, right? Because if I just trace this out, it's going to hit at that point because of the shape of the budget set. And so Hausman's insight, which is exactly right, is that you need to use this, what he calls virtual income y2, or if you're in this bracket, the virtual income y3, you need to plug that into the equation here when you're thinking about the guy's labor supply choice instead of always using y1. Okay, so that ends up mattering if there are income effects. Obviously, if gamma equals 0 and there are no income effects, this problem is irrelevant, right? Because your labor supply only depends upon the marginal wage. Okay, so this is somewhat of a technicality, but it ends up affecting the estimates that you will get. All right, so given that observation, let's talk about how we actually construct the likelihood function given a parameter vector, and then how you maximize it. So to make this simpler, suppose you have a 2-bracket system, right? So they're just 2 different tax brackets. So there's one kink. So what are the places an individual can locate? They can locate on the first bracket, they can locate on the second bracket, or they can locate at the kink, which I'm going to call L sub k. L sub k hours takes you to the kink, let's say. The likelihood is the probability that we see individual I choosing labor supply Li given a parameter vector. and we can decompose the likelihood into 3 components, which are the part for the first bracket, the part for the second bracket, and the part for the kink. Okay, so let's start with the first component. Let's take a person who in the data we see is on the first bracket, okay? So he's working like 10 hours and he's below the second bracket threshold. So 0 is less than Li less than Lk, so we empirically observe that. So then Li, for that person, given the functional form we've assumed, looks like this, right? Given the parameter vector, we predict that his labor supply, if we knew this error term, would be given by this equation here, where I use y1 as the unearned income, the actual unearned income. So now the next step is the way to think about this is I actually see him working 10 hours. If I ignore this error term, let's say I pick a set of parameters alpha, beta, and gamma, where I would predict he would work 6 hours. So it has to be the case that the unobserved error nu I is +4 in order to get us to the actual observed hours of 10. All right? So for each person, I can compute what the value of nu I is. Given, remember, always like assume that I've picked a value of alpha, beta, and gamma. I've picked a given parameter vector, and then we're going to loop over that. All right? So I can construct what nu I is for every observation in my data, right? Given an alpha, beta, and gamma. Okay, so then I can calculate what the likelihood of observing that error is, right? So I've got this normal CD, the normal density. If I get a nu I value that's super high, then I'm going to get a very low value for the likelihood, right? It's very unlikely that the guy's labor supply, the unobserved error, is 5 standard deviations above the mean. If nu I is a number near 0, then it's quite likely that he would have actually picked that level of labor supply. So I can compute each individual's contribution to the likelihood function in this way. Now I can do the same thing in the second bracket. It's exactly the same exercise, except instead of using y1, his actual unearned income, I use the virtual income in the second bracket because of the logic that I was describing before. Okay? And then I can take the people who I see at the kink, the people who are bunching at the kink. And so what property do these people have? It's like they don't want to be on the interior of either budget set, right? So if I just blow this up. Budget set looks like that. That's the kink. Okay, so these guys, if they're optimizing facing this schedule, like suppose this first bracket continued, they would pick a point that looks like this. So they would go beyond this level of labor supply. And if this budget set looked like that, they would pick a point over here. All right, so it's like they're not happy with the interior of either of these budget sets. On this budget set, if it extended out linearly, they would want to work more hours at that wage rate. Okay, so like here the wage rate is $10, here the wage rate is $5. At a wage rate of $10, I want to work more hours than I can and stay in that bracket. And at a wage rate of $5, I want to work less hours than I can in this bracket. Okay, and so as a result, I end up picking that kink. The tangency condition doesn't hold, but that's the best that I can do given the budget set that I face, right? So that's what this says here. If the tax rate is tau1, virtual income is y1, you want to work L greater than Lk. And conversely, if you're on the second budget set, if the tax rate is tau2 and the virtual income is y2, you want to work L less than Lk. That's the set of guys who are going to show up at the kink. Okay, so those two inequalities immediately tell you what the nu I has to look like for you to be within, in that bracket where you want to locate at the kink, right? There's going to be a range of the error term that's going to make you want to be at the kink given a parameter vector. And so, that's what these two inequalities are here. Let me not dwell on the math. The point is that the contribution to the likelihood of these people who are located at the kink is the probability that the error lies within this range where you're going to satisfy these two inequalities, where you want to work more than some amount, but less than some other amount, right? And so that's going to end up creating another contribution to the likelihood function. Okay, so then the logic is straightforward. In any maximum likelihood estimation, once you've constructed the likelihood, that's the most complicated part, you just sum the log likelihood. That's the same thing as maximizing the product of the likelihoods for each individual. And then the final step is what I was saying is like the looping step, right? That's the way you do it on a computer. You would max this function over this parameter vector. And the reason this stuff is usually quite complicated is once you have a lot of parameters, like if you have heterogeneity and stuff, this becomes a very high dimensional problem. And so now you're optimizing a function over a very high dimensional space, which is incredibly messy. Okay, but so yeah, in practice, the likelihood function is going to be more complicated because you're going to have many other components, but basic logic doesn't change. Okay, questions about that? All right. So Hausman applies that method to a cross-section from the 1975 PSID. He finds significant compensated elasticities and large income effects, larger elasticities for women than men, which is a pattern that we find very frequently in this literature and I think is actually robust. The shortcomings of this implementation, one you've already hit on, the sensitivity to functional form choices. The second is that the way Hausman implemented it, you actually have no tax reforms, okay? So it doesn't solve the fundamental econometric problem that taste for work might be correlated with the wage. So basically what he's assuming is that people differ in their wage rates and end up in different parts of this nonlinear tax schedule. But they do not have, they have this new I term, which is just some unobserved heterogeneity, but we are ruling out the possibility that the new I is correlated with your wage, which is actually extremely plausible. Like guys who have very high wage rates did not randomly end up with high wage rates. They probably, were really motivated, got a lot of education or whatever, and they have a high taste for work as a result. And so then you're going to get it totally wrong, okay? Because you don't have an orthogonality condition to identify this thing. And that, I think, is the problem that the bunching approach addresses head on. Okay, so then just a quick word on the way this literature developed. I'm not going to go through these studies in detail because I don't think it's the active part of the literature at the moment. So subsequent studies obtained different estimates. What really raised a problem is that a bunch of studies got negative compensated wage elasticity estimates, which doesn't make any sense because you can't have a Hicksian price elasticity that's actually negative, right? It's a deep problem because it's like rejecting the model that you are using to estimate the data, right? So you're implicitly assuming that people are maximizing utility, but a direct consequence of utility maximization is that the Hicksian elasticity cannot be negative. So when you get a negative elasticity estimate, you know that something is wrong. Okay, so that led to a debate about whether you want to impose the requirement that the compensated elasticity has to be positive. So one way to think about this is like maximum likelihood estimation with constraints. I'm not going to let this beta parameter be negative. I'm going to find the best parameter vector among the ones where beta has to be positive, okay? But the other way to look at it is that something's wrong with the model, right? Like the fact that unconstrained, you're being led to the situation where beta negative fits the data best shows you that something's fundamentally wrong with your assumptions, and this kind of backdoor solution of imposing that it has to be positive is not really satisfactory, which I think is the right way to look at it. So what's the fundamental source of the problem? It's that the labor supply model predicts that there should be a lot of bunching at these kink points. Lots of guys should choose to pile up at these kinks intuitively because wage rates are changing so much at these kinks, right? So when I jump from the 10% to the 25% tax bracket, that is a 15% reduction in my wage right at that point. And a 15% reduction in my wage should make a lot of people say, I don't want to work that marginal hour, I'm going to quit right when I get to that kink. The problem is, as I will show you in various examples, you observe very little such bunching in the data. And so the model ends up being effectively rejected by the data because it's predicting something that you don't see. And so the interest in these nonlinear budget set models sort of diminished, despite, I think, their very clear conceptual advantage over running a simple OLS regression. Okay, so the most recent work in this area focuses on the amount of bunching at kinks, where there's a paper that Emmanuel Saez actually wrote in 2002, published in 2010, and then has since developed in the context of this literature on frictions. Okay, so in this paper, Emmanuel observes that the only non-parametric source of identification for the elasticity in a cross-section is the amount of bunching at kinks. So what's the idea? If I only have a single cross-section of data, and I am not willing to make the assumption that the error term nu is orthogonal to wage rates, I'm not willing to take any stance on that, then any shape of the distribution that I just kind of see generally doesn't tell me anything about the elasticity, because it could have been generated by the underlying distribution of Tace. But the amount of sharp bunching at this kink actually does directly identify the elasticity, because it's kind of like a regression discontinuity. The slopes are changing sharply at that point. So as long as I assume that the heterogeneity in Tace is smooth, that is, there aren't jumps in this underlying distribution that's producing nu, which is the standard assumption we make in all non-parametric identification, then I can identify the elasticity directly from the amount of bunching at kinks. And moreover, and this is, I think, important, there is no further information to be had by imposing the rest of the structure of the nonlinear budget set model. Because if you have no idea what that distribution of nu I looks like, this is your one and only source of identification. So you might as well just directly map from the amount of bunching at kinks to the elasticity of interest. Okay, so what he does specifically is derives an estimator for the compensated taxable income elasticity using the amount of bunching at kinks, where he shows that, in fact, it's very simple. It's just the ratio of the excess mass at the kink divided by sort of the size of the treatment, the percentage change in the tax rate at that kink point. And that, I'll show you how you derive that formula in a second. That's become a very popular approach currently, because it turns out that when you connect this to the frictions issue, it yields highly credible estimates and gives you some insight into what's going on. Okay, so first of all, in the setting without frictions, how do you get this formula? So here's what the kink does. So in this diagram, which is from the Saez paper, this is just flipped relative to what I was showing you earlier. So the x-axis is pre-tax income or labor supply rather than leisure, right? So more you work, you're going to the right here rather than the left. And then this is after-tax income. So what the kink does is you're facing like a wage rate of $10 here. Wage rate falls to $5 at this point. Then you continue, right? Okay. So as we've talked about, there are going to be a bunch of people who collect at that point. And specifically, who are the people who collect at that point? It's the people who would have been closest to that kink if I had faced the linear tax schedule. So suppose I had the hypothetical linear tax, which is shown by the blue up here. Okay, they're going to be a set of guys who would have picked labor supplies that are relatively close to this kink that I'm about to introduce. Those guys all want to cut their labor supply. Everybody wants to cut their labor supply, okay, when I increase the wage. But the guys who are relatively close to this threshold, as we were talking about earlier, they're not going to go into the previous bracket. They're going to pile up at this point here. Now, the width of that interval, okay, the width of the interval of people who end up at that kink is directly related, of course, to the size of the excess mass of the kink, right? So if I see that 10 guys pile up at this kink, they must have been 1, 2, 3, 4, 5, 6, up to 10 ordered on that x-axis. So measuring the collection of excess mass at the kink is equivalent to measuring the width of the interval of the number of people who end up cutting labor supply and ending up at the kink when I raise the tax rate. So call the width of that interval dz, okay? And there's going to be a person who's just at that point z plus dz prior to the reform, so call that individual h in this diagram. He has an indifference curve which is such that he chooses z plus dz optimally before the reform and then just ends up at the kink after the reform. Okay, he's exactly that last guy who ends up at the kink. For this guy, one way to think about it is that the size of the DZ for that individual is going to be proportional to the extent to which I change tax rates multiplied by the elasticity multiplied by his initial income level. So if I have a bigger treatment, a bigger change in tax rates, okay, or I have a bigger elasticity, I'm going to be drawing people from a wider band of a wider range to collect at the kink, right? So think about it as, you know, I'm, let's say, going to collect 10 guys if the elasticity is 0.5, but if the elasticity is 1, the set of people that I'm going to collect is going to extend further to the right, right? It's going to be directly proportional. The interval of people that I move to the kink is going to be directly proportional to the size of the elasticity and the size of the treatment. And so that's why you end up getting this relationship that dz over z equals the elasticity times dt over 1 minus t, or in other words, this is just rearranging what I showed you on the previous formula. The elasticity can be written as dz over z divided by the size of the treatment. That is the excess mass divided by the size of the. So what happens when you introduce this kink, right? The entire distribution shifts to the left. So I think one thing that people often get confused about is it's not that only these guys in the z plus dz interval end up moving to the kink. All the other guys are changing their behavior too. It's just that you don't see it at the kink. And so this they're going to come and fill that gap that would have created. So there is not going to be a hole when you when you have a kink. There is going to be a hole when you have a notch, which is something we'll talk about later briefly. People have recently been studying these notches where you discontinuously lose in level terms when you cross the cutoff. So an example of that is like if I lose eligibility for health insurance when I cross a certain point, that's a notch because my budget set actually discontinuously falls down because I've actually lost money. And that's going to create a hole because you don't want to be the guy who's just $1 above and has lost health insurance, right? Okay, so you should go through this paper just so you understand exactly how you get this formula. But the idea is the size of the interval of people who you end up moving to the kink is proportional to the elasticity times the size of the change in tax rates. And then you invert that to get this formula for the elasticity in terms of excess mass divided by tax change. Okay? Okay, so Emmanuel implements that method using individual tax return microdata, the IRS public use files. IRS puts out these cross sections publicly, extract of the tax data from 1960 to 2004. A critical advantage of these data is that they have very little measurement error. So you can see that as soon as you have measurement error, the bunching method is going to be totally screwed up because you're relying very heavily on getting people's incomes exactly right around the kink. And he finds sharp bunching around the first kink point of the EITC for the self-employed, later shown to be due largely to reporting effects. So this is something that I showed you early on in the first lecture, a version of this from our recent paper. So this is just the plot of the income distribution around the EITC schedule, right? And the solid line here is for self-employed people, and you see this huge spike for the self-employed guys exactly at the first kink of the EITC schedule, which recall is the refund maximizing point. But if you look at the wage earners shown by the dashed line, there's really no evidence of excess mass right at the kink. Okay? And that's the zero bunching result that I was talking about before. And as we talked about in the first lecture, we think this is largely due to income manipulation, that the self-employed are able to report a different amount of income. In terms of real labor supply responses, we're not really seeing much. And that's what ends up rejecting the standard nonlinear budget set model. All right, so let me show you a couple of other examples of in the earlier literature before we get to the stuff which I think of as relating to the frictions agenda of how there are firm-side responses and sluggish adjustment and stuff that complicate the picture. So another good example of this bunching literature, early example, is a paper by Leora Friedberg on the Social Security earnings test, where she uses CPS data on the labor supply of retirees receiving Social Security benefits. She studies bunching based on responses to what's called the Social Security earnings test. Okay, what the earnings test is that above a certain exempt amount, you face a phase out of your Social Security benefits in certain age ranges. So if you're 62 years old and you earn more than $10,000, every additional dollar that you earn is going to lead to a cutback of your Social Security benefits, okay? And the phase out range varies by age group from 50%, 33%, and 0 for older workers where there's no phase out. There's no earnings test at all. So it's easy to see her results with these simple graphs which show you the exempt amount by this vertical line here, okay? And then she plots just a histogram of the percent of age group in earnings bins, $1,000 bins of, to show the earnings distribution around that cutoff. And you can see clear evidence that there's a piling up of people right at that kink point around the earnings test, where lots of people have decided that they don't want to work above that exempt amount. One thing that's kind of interesting about this is that there's no reason that you should try to keep yourself strictly below the earnings test threshold, right? Because this is not like a cutoff. If there's a little bit of noise, you should be just as happy to be $1 above as $1 below. But what's interesting about the pattern you see here, and I think in many other cases, is that there seems to be a collection strictly below, but not really just above. And I think that might reflect the fact that people misunderstand what the earnings test is. They think that if their earnings go, if some people think when their earnings go above the exempt amount, they're going to lose their Social Security benefits completely. You're going to see that pattern. But if they just thought, the extra dollar that I earn is going to be taxed at a higher rate, I lose a little bit of my Social Security benefits, they should not necessarily behave in that way. So that's kind of interesting because it shows you that in order to map this elasticity back to the parameter we care about, you really need to understand what perceptions of the tax schedule look like exactly around that point. If people are misunderstanding what the tax schedule is, you're obviously going to misestimate the elasticity. Okay, so that's Friedberg's study. She then goes on to estimate the elasticities using the Hausman method, finds relatively large compensated and uncompensated elasticities. You can see why, right? Because the amount of bunching is fairly large. There's a more recent paper that uses better data, admin data, and by Hayter and Lofgren. They replicate the Friedberg results using more years and using administrative measures. And as you'd expect, related to what I was saying earlier, they find that the degree of bunching and implied elasticities are 3 times larger when you have less measurement error. Because as soon as people are misreporting their earnings and hours of work, the thing is going to become diffuse and you're going to understate what the true elasticity is. Now, what is really ironic about this whole thing is that this is one case where I think you actually find pretty clear evidence, even not doing all the corrections for frictions that we're going to talk about. Just directly, the basic graph, you see clear evidence that people are responding to incentives. But what's really weird about it is that you actually are not losing your Social Security benefits when you cross that kink. All that's happening is that you get them in the future at an actuarially fairly adjusted rate. So every dollar that you have held back at age 62, you get back at age 70 with an adjustment for life expectancy and interest. That's actually perfectly fair. And so, strangely, the one kink where you do actually find real bunching in the literature is not, in some sense, a real kink. That is, people have misperceived it to be a kink. So, all of this stuff, you can see where this is building. Like, I think the perceptions and adjustment stuff is absolutely crucial here. But so let's, so stepping back, why do we not see more bunching at kinks in general? Like, if you just plot the US income distribution as a whole, you have various cutoffs, as we saw, various kinks in the US tax schedule. The distribution just looks totally smooth. So why is that? Okay, so one view is that the structural elasticity, the underlying elasticity, is actually super small. In fact, it would have to be like very close to 0, given the amount of data we have. We can say with precision, if we apply the Saez formula, that the structural elasticity would be near 0. So, that's obviously one possible explanation. Another explanation is that it has to do with noise in the income generation process. So suppose the model is one in which I can't pick exactly how many hours I work and exactly what my earnings are in order to target the kink. It's probably more realistic for more people is like, there's some chance I get an extra overtime job, I might get laid off, I have various shocks to my household income, so I don't have perfect control over my income, right? And that is not going to produce sharp bunching, right? Both because of the mechanical effect that I'm adding noise to the distribution ex post. That kind of functions like measurement error. But what's different from measurement error is that I'm also optimizing relative to that. So I know that there's no point in perfectly trying to target the kink because, there's some chance I'm going to have like a bigger deduction, mortgage interest deduction or whatever. There's some noise. And so I'm going to take that account if I'm optimizing, I'm going to take that into account when I choose my labor supply. So in principle, this could explain why we don't see much bunching. But in practice, it doesn't really do the job. And that's shown by this diagram here from a simulation in Emmanuel's paper, where he's looking at the kink from 15 to 28%. And for two different levels of the true elasticity, he's simulating what the distribution would look like if we had shocks to income of different amounts. And the way he calibrates the shocks to income is to match the year-to-year fluctuation that we see in income for people in practice. Okay, so sigma equals 2,000 is a plausible level of variation. Sigma equals 5,000 is relatively high. Now what you can see here is what this does is it doesn't produce the sharp spikes that we'd expect to see if there were no uncertainty, right? So it takes that away. But there are still very clearly visible humps in the income distribution. So the point he's trying to make in that paper is that even if you have a fair amount of uncertainty in the income generation process. Now, obviously, if I make sigma arbitrarily large, like if I make it infinity, I'm going to completely drive this out. So that's clear. But for a plausible level of uncertainty, calibrated to match the data, you would still, if people were optimizing in this way, clearly see pile-ups around these kinks. They wouldn't be so sharp, but they'd be these clearly visible humps. And so I think people's understanding is that it's unlikely that this second explanation is actually what's generating the small elasticities. What we'll talk about in the next lecture are price misperceptions, salience effects, and frictions, which I think is what's actually going on.